We now turn to section 5.7. We're going to talk about a new idea that's related to vector fields and some of the applications with flux that we saw in the last section. Now, to start this section, we need to define actually a new operation that we can do to a vector field. So take a look at the definition we have here. Suppose that F is a vector field that has formulas P, Q, and R in place of the different components. Now, if that's a vector field defined on R3, then, if I was to go ahead and take the partial of P with respect to X, partial Q with respect to Y, partial R with respect to Z, if it's the case that all of those exist, then we define the divergence of F as the following. It's a function, divergence of F, that is going to be the sum of those partial derivatives. So symbolically, we actually write div of F, or we kind of use this gradient notation, dot F. So notice that's not gradient of F, that's gradient dot F. So this is kind of a weird thing. This really isn't gradient. In fact, it has a different name. So to help ourselves remember this formula, you can introduce what we call a differential operator. And that's what we call del. So that's what this symbol is. And you can imagine it as a vector with these three components. Like, take a partial derivative with respect to x, but we just haven't specified what we're taking the partial of yet. Same thing with respect to y, and same thing with respect to z. Well then, when we think about the divergence of F, we can think about it as taking this partial derivative setup, del, and dotting it with our vector field of F, and we get this dot product, which then of course when combined means that I would take my partial with respect to X of P. So that's what I'd be applying that to, and that's where we get this divergence of F from. Now you don't have to remember it that way. Some people choose to and some people don't. But this del operation will be advantageous in the next section as well. Well, let's look at a couple examples here really quickly to see a little bit about what this divergence is, what it's good for, and why we care. First, let's just focus on the computation. Let's consider the vector field F that's given by this. Well, if I want to find the divergence of F, this should actually be super simple to do. My divergence for F is just going to be to go to each one of my components and take the partial derivative with respect to x, then y, and then z. So let's see, my partial with respect to x is going to be z for the first component. Partial with respect to y is going to be xz. And partial with respect to z over here is going to be 0. So in total, my divergence of f is going to be z plus, oops, that's not a plus, z plus x times z. So this is it. The calculation itself of this divergence is very, very simple. But what is it good for? Well, here's the application. In the context of fluid flow, which we talked about in the last section with flux, if F, again, the vector field, is measuring the velocity of the fluid at any given point, and of course its direction as well, then the divergence of F represents the net rate of change with respect to time of the mass of fluid flowing from a point per volume. So in other words, this divergence of F is the extent to which there is more exiting an infinitesimal region of space than entering it. Okay, to try to understand a little bit more about what this means, let's go ahead and write some of the following. So we'll say, therefore, if it's the case that the divergence of F is positive at a point, then we call that point a source. So again, this divergence is a way to help us try to understand that at a specified point, at that infinitesimal region in space, is there fluid that is emanating from that region? That is, the divergence is positive and I have a source of fluid flow extending from a point. Or is it the case that the fluid is kind of being sucked in? So here you can kind of imagine that if I had a point out in space, by saying that it's a source means that fluid flow is kind of extending out from that particular point. That's a source. Now, if I want to go ahead and say that my divergence of f maybe comes out negative, comes out less than 0 at a point, then we call that point a sink. So that is, at that particular point in space, fluid is kind of being pulled in towards that point as opposed to being extending away from it. So I kind of can think about every point as a source point or a sink point. And the divergence can help us understand which is which. Of course, it's also possible, though, that I don't get a negative or a positive number when I calculate the divergence, but maybe I get exactly 0. And if this happens at a point, then this point contributes nothing to the change in fluid flow, or the rate of fluid flow. If the divergence is 0, it kind of means there's nothing that's exiting or kind of entering that particular point. Liquid isn't being pushed away and it's not coming back in. So this is the purpose of the divergence. Now, if you take a look down here at example 2, we can get a sense of how we can determine where we have sinks and where we have sources with this little example. So suppose that I have the following vector field, and I want to determine at which points we're going to be considering sources, which ones are sinks, and which might be neither. Of course, to do that, it might be helpful to go ahead and just quickly calculate what my divergence of f actually is. So remember, I'm going to do partial with respect to x plus partial with respect to y. Notice here, though, this is negative, so I'll have to account for that. And then finally, my partial with respect to with respect to z. So what I end up with here is a formula of y minus x. Okay, so I can go ahead then and maybe start to reach some of the following conclusions. I can say that my divergence of f is definitely going to be equal to 0 if y is equal to x. So if I'm looking at all of the different points, oops, let me actually not bother drawing this by hand since I can go ahead and use this cool tool. But if I was to go ahead here and think about the xy plane, I can see then that along my line y equals x, right, along this line here, all of the points that are on that line are not sources, nor are they sinks, because the divergence at every point along this line is going to end up being 0. Okay, but what about points on other sides of the line? Well, let's see. We could say here that my divergence of f would definitely be positive if it was the case that y was bigger than x, right? Because then I'd have big value minus small. So that would mean that over here, where y's are bigger than x's, what I have are a bunch of sources. So these are source points. Now I can also see that if it's the case, or if my divergence is going to come out negative, that has to happen when, well, I guess my y would be less than my x. And so that would correspond to all the other points on this side. And so these over here would be considered my sink points. So fluid would be emanating from points out in here and kind of being attracted towards or being sucked in over on points on this side. So we can see here that z ultimately had no impact on the divergence here. And so therefore we can categorize all points in the xy plane and as these sources and sinks, and kind of imagine that if we were to stretch this, if we were to lay this flat on the table and then stretch points above and below it, that everything would stay the same. So the z coordinate has no impact here ultimately. If I move from a point here and I go up or down in terms of z, I still maintain my point as a source or a sink. So in the next video, we'll take a look at what exactly we are going to plan to do with this concept of a divergence of a vector field and why exactly it can relate to the topics that we've talked about in the past couple sections.